Okay. No, I'm going to make live streaming in YouTube. Yeah. Now it's done. Okay. So Prita, can you check? I'm going to make live streaming in YouTube. Okay.
Good afternoon, Ibu Rino.
Good afternoon, everyone.
Good afternoon.
So Rino is one of your fans.
Yeah, we have been to several conferences together.
Yeah, that's true.
Oke, bisa semuanya di admit.
Maaf, belum bisa ngilangin background.
Ya.
Belum.
Gimana Bu Gigi?
Ini pakai tab jadinya lagi agak gaptek.
Susah. Saya juga.
Tab nggak bisa kok biasanya.
Nggak bisa ya?
Selamat sore.
Selamat sore Pak
Nengah. Apa kabar Pak?
Baik.
Sudah sore ya Pak di Bali?
Masih pagi Bu.
Oh masih.
So Professor PIRZADA, so we invite all of our colleagues in Indonesia, and also this open to everyone overseas as well.
Sure.
So some of them from Malaysia also registered to this event.
That's nice.
And yeah. Have you downloaded the virtual background successfully? No, Professor PIRZADA? In the chat room, the virtual background. If you like, you can download it and use that.
So what I have to do? Yeah, this is. Yeah.
There is a virtual background in the chat. Ada Bu Hilda. Here that.
Sudah ada saya ini lagi ya. Perlu saya mungkin untuk yang baru datang.
Diumumkan aja.
Ya.
Oke. Pak Joko sehat kan Pak Joko?
Alhamdulillah Pak Edy.
Sehat ya.
Jadi saya itu Pak Edy dan teman-teman.
Ya.
Jadi waktu kita mau waktu Tendik mau mau check up itu ya. Kan mau ditutup tuh kampus selama 5 hari 1 minggu. Saya ke kampus tanggal 29. Saya mau pinjam buku nih. Ada buku yang mau saya pinjam. 2 hari kemudian itu Dwi yang perpustakaan keluar tes PCR-nya positif.
Tapi Pak Joko nggak apa-apa kan?
Enggak. Jadi saya
ini sudah live di YouTube loh. Ini sudah live di YouTube.
Kita ngobrol, jangan ngobrol ya.
Sudah live di YouTube.
Sudah ini ya. Sorry.
Sudah on ya di YouTube. Oke.
Dua lewat.
So, Professor PIRZADA, are you ready?
Yeah, I am ready.
Yeah, ready?
Yeah.
Okay, so I think we can start now. Yeah.
Yeah, we can start.
Bisa minta tolong mute-kan semuanya. Apa tadi? Devi, tolong Devi ya. Okay, so good afternoon, everyone. Thank you for joining us in Combinatorics today's series. This event is organized by our group, Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi, Bandung. And in this afternoon, we are very, very delighted to have Professor SHARIEFUDDIN PIRZADA as a keynote speaker. He's from the University of Kashmir, Srinagar, Kashmir, India. And he will speak on the Laplacian Eigenvalues of Graf. And before I give a short CV of Professor PIRZADA, I would like to invite Dr. Joko Supriyanto as the chairman of our research group to give an introduction remark. Please welcome Pak Joko.
Okay, thank you. Thank you very much, Pak Edy. Good afternoon, everybody. Again, welcome to the Combinatorics today's seminar. And as you have known, that this program is a seminar series conducted by our research group, Combinatorics Mathematics Research Group. And hopefully we can organize this event as a monthly seminar in Combinatorics with speaker, hopefully from all over the world. And our special thanks to Professor SHARIEFUDDIN PIRZADA to become the first speaker in our Combinatorics seminar series. And just for your information, Professor PIRZADA, almost all of combinatorialists here in our country are working in graph theory, but so far, none of them works in algebraic graph theory, in particular in spectral graph theory. Although I believe that many of us are very interesting in this interesting and very hot topic in graph theory. Therefore, you are among the most wanted speaker for our seminar. And also, I would like to thank to the participant of this seminar, and we do hope that you can enjoy the seminar. And I think the recorded version of the seminar will be available later, right? Rita, yeah? Okay, that's all from me, and enjoy the seminar. Thank you.
Okay, thank you, Pak Joko. So now I'm going to read a short CV of Professor SHARIEFUDDIN PIRZADA. So he's a professor at the Department of Mathematics, University of Kashmir, Srinagar, Kashmir, India. And he's currently the Dean of School of Physical and Mathematical Sciences since 2017 up to now. And also he's just appointed as a head of Department of Mathematics. Is that right, Professor PIRZADA? Yeah. And he's also taught at King Fahd University of Petroleum and Minerals a couple of years ago. And his research interests in combinatorics and graph theory, as well as algebra. His Scopus its index is 11, and his EDOS number is 3. And he has produced 10 PhD and 4 MPhil graduates. He has received a number of prestigious awards and fellowship, not only from India, but also from overseas, for example, from ITB, from IMU, ICM, Clay, and others. And he wrote a number of books and book chapters in graph, geometry, and combinatorics. He's principal investigators in various research projects. Almost every year he's got a research project from India, also from other countries, from overseas. And he has a lot of productive international research collaboration. And of course, he's members of editorial board in various reputable international journals. So without further ado, please welcome Professor PIRZADA. Time is yours. Yeah.
Masih unmute nih.
Okay.
Yeah.
Thank you very much, Professor Edy, for your kind words and kind introduction. And also, I'm grateful to all of you to invite me in this lecture series group. I was really happy when you asked me to be available for a lecture. And it is like I had been to Bandung, and I have some memories of Bandung also. So today I will talk, as you rightly pointed out, about the algebraic graph theory. And since the inception of this algebraic graph theory, what was the progress? And I will mostly focus on some current problems. So I will try to share my screen first, and then I will go ahead with my presentation. Okay, so as you see from the title of my talk, it will be about the Laplacian eigenvalues of graphs. Now let's start looking backwards. When some 100 years back graph theory was discovered, it was mainly because of two problems. One was the well-known Königsberg bridge problem by Euler, and the second was the Cayley's formula for trees. Initially, Cayley used to work on the hydrocarbons. He was interested in getting the isomers of such hydrocarbons. And later on, time passed, several new directions came into existence, and some 4 decades ago, this algebraic graph theory also came to the forefront. So the reason for this algebraic graph theory initially was like, supposing we have a graph or a network, and imagine if our graph is very large. So how to store it on the modern computer? Even the computers were not sufficient to store large graphs. So what graph theorists used to see, is there any representation of a graph where we can use less memory? So the situation is, we have a physical problem or a mathematical problem. We model it by a graph. And if somehow the graph turns out to be large, then the problem is how to represent it without having complications. And in this direction, linear algebra was used, namely the matrix theory was used, and graph theory started representing a graph by several types of matrices. So this was the goal initially, just to represent a graph by a matrix so that we have more and more information about the structure of the graph. And it was started with the incidence matrix, where incidence relation of the graph was involved. And later on, it was carried to adjacency matrix, where adjacency relation was used. And then several other matrices came into existence, like the cycle matrix, and then the Laplacian matrix, the distance matrix, the distance Laplacian matrix, to name a few. As of date, many new matrices have also come into existence. Like more recently, some years back, people started working on arithmetic geometric matrix, which is also related to a graph. Then the second is the geometric arithmetic matrix. And more recently, one matrix was, it's just some maybe months earlier, Somber matrix was introduced. There came one paper on Somber matrix, and we were lucky enough to contribute something towards it. Now, some matrices come directly from pure graph theory. Some matrices come from the indices, topological indices used in graphs. Like when I said Somber matrix, it came basically from Somber index. Somber index is a term which is used in chemistry. And then we have the Randic index in a graph. Then the Randic matrix came into existence. So
Excuse me, Professor PIRZADA. The slide is not changing?
No. I'm just giving the introduction.
Yes. Okay, good.
So what happened, having so many matrices, then what will be the line of action? Okay, we have a matrix, whatever type of matrix it is. What to do with the matrix of the graph? What to do with the matrix of the graph? Sorry. So what to do with the matrix of the graph? As I said that it was initially the representation, but later on, it had some deep involvement. Like once we come to the linear algebra part of this graph theory, once we have the matrix, instantly we switch to its linear algebraic properties. One such property is forming the characteristic polynomial. And knowing this characteristic polynomial or characteristic equation, instantly we go to the roots of that characteristic polynomial, which we call as the eigenvalues of the characteristic polynomial or the eigenvalues of the matrix. So initially, the matrix has been obtained from the graph. Imagine if we have the adjacency matrix, it has come out from the adjacency relation of the graph. Adjacency matrix is a square matrix. We have the characteristic equation. We get the roots of that characteristic equation, which become the eigenvalues of that matrix. And we call them as the adjacency eigenvalues because it has its history from the adjacency relation. Or more briefly, we say it is the spectrum of the adjacency matrix or spectrum of the graph. So spectra of a graph is nothing but the eigenvalues of its adjacency matrix. So there is enough material available with this adjacency matrix, and not only from the theoretical point of view, but applications. It has enormous applications in different areas of mathematics itself and other branches of sciences. Even social sciences have been also touched. And a similar type of matrix, which I will discuss in this talk, is the Laplacian matrix. So again, this is a square matrix. Again, I will be interested in the spectrum of this matrix. And then the question is, how much information we get from this spectrum? We call it as the Laplacian spectrum. So it will be a sequence of events like adjacency spectrum, Laplacian spectrum, signless Laplacian spectrum, and so on. For the time being, we'll be interested in this Laplacian spectrum. So during this talk, I will have some basic definitions and basic requirements about the Laplacian spectrum or Laplacian eigenvalues of graphs. And then I will discuss two important problems which are currently unsolved, not fully solved. One will be the Brouwer's conjecture, and second will be the Laplacian energy conjecture. And in case I get time, I will switch to some other problems also. So as I mentioned about the adjacency matrix, let's put the definition here. It's a square matrix with n rows and n columns, where n is the order of the graph, and the ijth element is defined as 1 or 0, according as the two vertices are adjacent or not. So it's very simple to construct this matrix. We have a graph. We have two possibilities between a pair of vertices. Either they are adjacent or not. They are adjacent, it is 1, otherwise it is 0. So I can say this matrix is a binary matrix. It is a 0-1 matrix. Now let's see what we mean by this Laplacian matrix of a graph. It's like a combinatorial form of matrix. It's again a square matrix of order n, where again this n is the order of the graph. And now let's look at the elements of this matrix. We see that it is split into 3 cases. Now, all the diagonal elements here will be di, that's the degree of the vertex, which was not present earlier in the adjacency matrix. Their diagonal elements are all zeros. So this is involved here. And secondly, the change here is if the 2 vertices are adjacent, it is now -1. It has its own sense. Why not +1? Because we will land nowhere if we take it as +1. Or either we can get a different type of matrix which is yet to be explored. And if the 2 vertices are not adjacent, then it's 0. So these di's are the diagonal elements, or we can say if we take this, the matrix whose all diagonal elements are the vertices of the degrees, then it will be our this diagonal matrix. All other entries are 0. Diagonal elements are degrees. Then this Laplacian matrix can be redefined as the diagonal matrix minus the adjacency matrix. So this is the alternative way of defining this Laplacian matrix. That is, instead of giving the initial definition, we can directly obtain this matrix from the adjacency matrix and the degree matrix. Okay, let's assume that we have this Laplacian matrix. We will have the characteristic polynomial, which will be of degree n. And by fundamental theorem of algebra, it will have exactly n roots. And these n roots will be called as the Laplacian eigenvalues of the graph. So now onwards, we'll go on repeating this term, the Laplacian spectrum or the Laplacian eigenvalues. So here we have an important thing to note. Once we have these Laplacian eigenvalues, what amount of information we can say about the structure of the graph? That's important. The more information we get from the eigenvalues, the stronger our case will be. Similarly, how these eigenvalues can be used to study the real-time problems. Okay, we know that this matrix is always real symmetric, it is positive semi-definite, and it is always singular. Since this is real symmetric matrix, its one eigenvalue is always 0. So we don't bother about the least eigenvalue, it's always 0. And we are left with now the remaining n-1 eigenvalues. Now, as I said that these eigenvalues give some information, but the main issue is how to get these eigenvalues. Imagine if we have an equation of 4th degree or 5th degree algebraic equation, it's very hard to get the roots by simple methods. And here we say that our graphs are very large. Imagine a graph of order 100 will yield the equation of degree 100. And we can guess what complicacy will be involved in getting the roots of that equation of degree 100. So the first issue with us will be, is there a way to get all these eigenvalues? If we get all these eigenvalues, fine. But what if we are not able to get all these eigenvalues or even some of the eigenvalues? Then we never stop there, but we go on discussing the location of these eigenvalues, where they will be located. That's also an important aspect of research in this area, to discuss the location of eigenvalues or the distribution of eigenvalues or Laplacian eigenvalues in our case. From here onwards, we will denote these n Laplacian eigenvalues by mu1 so on to mu n. And we take the smallest one as mu n, as is indicated here. Mu n is 0. This is the smallest one. And this mu1 is the largest one. Now, the importance of this largest one is, in case if we take the adjacency matrix, there is again the largest largest eigenvalue. And that largest eigenvalue is called the spectral radius of the graph. So it has a spatial connection. The largest eigenvalue, adjacency eigenvalue, is called the spectral radius of the graph. And analogously here, the largest Laplacian eigenvalue will be the largest Laplacian spectral radius. So if we take the sum of these Laplacian eigenvalues without individually calculating them, it comes out to be the trace of this Laplacian matrix. And this trace is always the sum of the degrees, which is always twice the number of sides of the graph. That is the number of edges. Okay. Now this Laplacian matrix has an important connection with this theorem, which is called as matrix tree theorem. We teach this matrix tree theorem in the undergraduate classes. So this Laplacian matrix is also called as Kirchhoff matrix because of its role in the matrix tree theorem. The name is because it is attributed to Kirchhoff. So what was that theorem? It is the theorem of 1847. If we have a connected graph with n vertices, then all the cofactors of this matrix LG are equal, and the common value is the number of spanning trees in G. Very interesting result. So given a connected graph, we say that it has at least one spanning tree. But the question always remains, what is the number of spanning trees in a connected graph? There are several methods like recursive methods, methods by construction, not strong enough. Usually they take much of time. So this one is using the algebraic part of this graph theory, how to get the number of spanning trees of G. And here it's important to mention that this the number of spanning trees in a connected graph G is called the complexity of the graph. So the complexity of a graph is always the number of spanning trees. We have several other names for this Laplacian matrix, like the matrix of admittance, which usually comes from electrical networks. The electronics, the electrical engineers use this type of notation. We can again reform this definition of this Laplacian matrix. Let's take a connected graph, or need not be connected. We orient the edges. Like we have a directed graph where already the direction is given. But here, given a graph, let's arbitrarily orient its edges, give some direction to each edge. Then the oriented incidence matrix formed by giving the orientations is defined as the matrix C, where the elements are +1, -1, or 0, according as the edge is outgoing or the edge is incoming. Now, how it has come, this outgoing edge or incoming edge, this is because the direction is now there. The edges have been oriented. So we cannot say in simple graphs, if there is an edge between U and V, it's same as saying it's the edge from V to U. It's symmetric. But when we give direction, then we say the edges from U to V is different from the edges from V to U. They have different sense. That's why we take this word edge as the arc in the directed graph. So once we have oriented the edges, it looks like a directed graph. So we have outgoing edge, we have incoming edge. So we put the elements accordingly as +1, -1, and 0. So this is our matrix C, a matrix which is called as oriented incidence matrix. Now what happens? Now multiply this C with its transpose. Once we multiply C with its transpose, it's nothing but the Laplacian matrix. So we can see we have another direction of defining this Laplacian matrix. That means these equivalent definitions, sometimes if we are not able to get some property of the Laplacian matrix directly, we come, or the graph directly, we come along these types of definitions to attack the problem. Now, as I said that the smallest Laplacian eigenvalue is 0, and the question is it necessary that there's only one 0 as the Laplacian eigenvalue? Not necessarily, really. It can be it can be of larger multiplicity, means 0 can be repeated several times. And Fiedler found it that if 0 is of multiplicity greater than 1, the graph will have such number of components. So if a graph is disconnected with 3 components, so it will have 3 Laplacian eigenvalues as zeros. That's why this Fiedler, in his result in 73, he showed that a graph is connected if and only if its second smallest Laplacian eigenvalue is positive, and called it as the algebraic connectivity of the graph G. Now look, the smallest one is always 0. It's true for connected graph as well as disconnected graph. But if it has more than one 0, it will have more than one component. So we usually don't deal with this, the smallest one. We deal with the second smallest one. If second smallest one is positive, the graph will be always connected. So that's why the second smallest one is usually called as algebraic connectivity of the graph. Okay. Now, as I said that we'll be first of all interested in getting these Laplacian eigenvalues, and we do it with some standard type of graphs, like we can discuss about the cycle, the complete graph, the bipartite graph, the complement of a graph, because these will be frequently used in our investigation of the research in this area. Now, once we know the graph G, we have the complement of this G, and we can see the Laplacian eigenvalues of this G complement are, as are mentioned here, they will be 0, n minus mu1, and so on. Keeping note that this mu1 and up to mu n minus 1, they are the Laplacian eigenvalues of G. So from Laplacian eigenvalues of G, we get Laplacian eigenvalues of the complement. Okay, if the graph G is connected and has components Gi, rather it's disconnected graph with components Gi, then the spectrum or spectra of G will be the union of all these spectra. So let's come to the complete graph Kn, which is a graph having edge between every 2 vertices. So by calculations, we have found out that the Laplacian spectrum of this complete graph is n. This is not the power here. This will be the multiplicity of the eigenvalue. That means this n is repeated n minus 1 times, and the last one is 0. So in other words, we can say the Laplacian eigenvalues or spectra of the complete graph will be n minus 1 times, and 0. So with that analogy given earlier about the complement, this complement of the complete graph, its all eigenvalues will be, Laplacian eigenvalues will be 0, because this is an empty graph. The complement of the complete graph is always an empty graph. In case we discuss this complete bipartite graph with parts having cardinality as m and n, we first calculate the Laplacian spectrum of the complement. Now, interesting thing to note here. I didn't mention the complete bipartite graph, what will be its Laplacian eigenvalues. Instead, I am going to the complement, because I can get the Laplacian eigenvalues of the complement very easily. Now, how? We note that this complement is always the disjoint union of 2 complete graphs, Km and Kn. So if we take the disjoint union of Km and Kn, now Km is a complete graph, Km complement is an empty graph, so it's one empty graph. Kn is a complete graph, its complement is second. And now, when we take the disjoint union, it means we have to take like this. So you can see the Laplacian eigenvalues of Km are here, Kn are here, and 0 will be here 1, 0 will be here 1, so 0 will be repeated 2 times. So we have n repeated n minus 1 times, m repeated m minus 1 times. So once we know Laplacian eigenvalues of the complement of bipartite, complete bipartite graph, we can just evaluate and get the Laplacian eigenvalues of the complete graph by the earlier method where it was n minus something, and so on. Okay. We can observe that there is always a very reasonable connection between the diameter of a graph and the number of distinct Laplacian eigenvalues of a graph. And if we come to the diameter, it comes from the distance. We say that the distance between two vertices is the length of the shortest path. And then we have the radius of the graph, and we have the diameter of the graph. We have the eccentricity of the graph. We say the radius is the smallest eccentricity, and the vertex where we have smallest eccentricity is called the center of the graph. So in other words, roughly we can say it is the farthest vertex from a vertex. So now to get this diameter, if we say it is the farthest vertex, but distance is always measured by the shortest path. So we have to go by the shortest path. Now, what is the link between this diameter and the distinct eigenvalues? Here we have the link. This is very interesting result here. If our graph is with diameter d, then this g has always at least d plus 1 distinct Laplacian eigenvalues. We were talking about Laplacian eigenvalues like mu1, mu2, and their multiplicity, but we didn't know how many are repeated. And if every Laplacian eigenvalue is different, means they are distinct eigenvalues. Here, this result gives the information. Assuming that diameter is d, then it has always at least d plus 1 distinct Laplacian eigenvalues. Not only the result is applicable for Laplacian, it is applicable for the adjacency also, and the signless Laplacian also, which we discuss at the end of the talk if we get time, the signless Laplacian. Okay, now, as we see, the eigenvalues or the Laplacian eigenvalues can be any numbers, they can be any real number. The issue is it possible that we have graphs whose this Laplacian spectrum is always integral? That means they are always integers. Yes, of course, there are graphs whose Laplacian eigenvalues are all integers. Those graphs are called as Laplacian integral graphs. Some cases we discuss here. First of all, we note this relation. If G is Laplacian integral, then its complement is also Laplacian integral. The earlier relation I have given between the graph and the complement of the graph. Now, if we have a star, obviously star is a tree with common vertex and all other vertices are connected to this common vertex. This star is complete bipartite also. It's K1D for some D, which we say also as the claw center, something like that. So the statement is this tree T is Laplacian integral if and only if T is a star. So any tree, so this has closed our doors. Any tree is Laplacian integral if and only if it is a star. So there are no other trees other than star which are Laplacian integral. Okay, some more types of graphs, like we have a graph Gn, which is obtained by subdividing one edge. Now, usually subdivision we do in planar graphs, where we call them as the homeomorphic graphs also. So we have a graph, we take one edge arbitrarily and subdivide it, put a vertex somewhere on that edge, it makes two edges. And if we take the complete graph with n-1 vertices, so kn-1 is there, we subdivide one of its edges, we obtain this graph Gn. We don't have any name for this graph, we just say it's Gn. It has been obtained by subdividing an edge. Then Gn is Laplacian integral. This has been verified also. The reason is that Gn complement has two connected components. One is K2 and second is the star type K1 n minus 3. Since both these are Laplacian integral, so these two give rise to Gn bar. The complement, this complement is integral, and by the previous result, Gn is also Laplacian integral. So this Gn bar, if we construct this Gn bar, we'll see that it contains two components. One is K2, sorry, one is K1 n minus 3. Now this one is Laplacian integral. K1 n minus 3 is Laplacian integral. There, when we take their union, that's Laplacian integral. So it means Gn complement is Laplacian integral, which by one of our earlier results, Gn is Laplacian integral. We define another type of graph, which is a generalization of this Gn. It's SG. It's obtained from G after subdividing every edge of G. So here we don't have any restriction on G, and we don't have restriction to subdivide only one edge. We divide all the edges and we get SG. So Ground and Maris in 1994 observed the following, which says that this G is a connected regular Laplacian integral on n vertices. We are given that G is Laplacian integral with order n, and the observation is that this SG, which has been constructed above, is Laplacian integral if and only if this G is isomorphic to the complete graph. So again, with respect to this SG, the chapter is closed. So we have the necessary and sufficient conditions. Some more types of graphs which will be useful in those two problems which I mentioned. I will focus on those two problems. One graph is called as cograph. So let's see what is a cograph. So it's always a graph which does not contain path on four vertices as an induced subgraph. So any graph which does not have induced subgraph as P4 is called as a cograph. K1 is obviously a cograph. Also noting that if G is a cograph, then the complement is a cograph. If there are two cographs, G and H, their union is also a cograph. And we have seen that the Laplacian spectrum of a cograph is always integral. All the Laplacian eigenvalues of cograph are integers. Another type of graph is called as the split graph. It is like we have two graphs. One is, or we can say when a graph is said to be a split graph. So how to characterize of a graph being as a split graph? So if this graph can be partitioned into two parts, so that one part is a clique and the second part is an independent set. Clique is the largest complete subgraph, and independent set is no two vertices are adjacent. So we can see from the figure here, this is a complete subgraph and this is an independent set. So if we can do this partitioning for a graph, it's called as a split graph. And the split graph is complete if there is an edge, which are represented here by dotted lines. So you can see in split graph, it is not necessary that there are edges from every vertex of K to each vertex of S. But if we take complete split graph, then there should be an edge from each vertex of K to every vertex of S. So we have two types of graphs. One is split graph, one is complete split graph. This graph is also referred to as the split partition, and it is usually denoted by KS like here, because this K means it is the clique and S means the independent set. It's also called the polar graph. There is an observation about this split graph. The complement is also a split graph. Every induced subgraph of a split graph is split. And next graph is, which is called as the threshold graph. Once again, one of the important graphs in doing this Laplacian eigenvalues property. So this graph is, if it has no induced subgraph, which is isomorphic to P4 or C4. So like an extension of the cograph, there only P4 was missing. Here P4 is missing, C4 is missing, and twice K2 means two copies of K2. They are missing. if we don't have such induced subgraphs, we say that the graph is a threshold graph. It's also called as degree maximal graph, and this can be constructed as follows. So someone will be interested to see how we can construct such a graph, threshold graph. Very simple. So just take two operations, start with a single vertex. From a single vertex, just add a dominating vertex or add an isolated vertex. So at each stage, either add a dominating vertex or add a isolated vertex. You will stop somewhere. The resulting graph will be a threshold graph. Now, we discuss these types of graphs not only because they are important in their own respect, but they are used in improving certain types of results here. Okay, some techniques from matrix theory now, which are also oftenly used in proving results from this spectral graph theory. So majorization, we are all familiar with this majorization technique. If we have two real sequences x and y, and both are of length n, then one is majorized by another if these conditions are true. So we have these conditions here with these two sequences. What happens with this majorization technique? The spectrum of Laplace matrix and majorization, they are connected by a relation, which is a majorization relation between the eigenvalue spectrum and diagonal elements of Hermitian matrices. So this again will be like when we come to Hermitian matrices, or when we take the spectrum of Laplace matrix, we can find this connection. Then interlacing property, again from the matrix theory point of view, if we consider two real sequences, the length is here and the second sequence is said to interlace the first sequence whenever we have the following conditions getting satisfied. So one is majorization technique, another is interlacing. So this interlacing will be tight if the conditions for here, if the equality holds here, xi equal to yi, and this yi equal to xn minus m plus y, then we say the interlacing is tight. Again, one of the reasonably good concepts from matrix theory, it's Schur's inequality. It's again related to majorization theory. For that we have, so these techniques don't use graphs. They are just the concepts from matrix theory. If we have A as a real symmetric matrix and having its eigenvalues as lambda 1, lambda 2 to n, and then diagonal elements are d1, d2, dn, then it means summation of di is always smaller or equal to lambda I, which means the majorization takes place here between the diagonal elements and the eigenvalues. So there's a majorization relation between the diagonal elements and the eigenvalues. Okay, now let's focus on this concept. We have this d equal to d1 to dn, where d1 is bigger or equal to d2 and so on. It is the degree sequence of a graph. We start with a degree sequence. So this is like, this one is the largest, this one is the largest degree. So it will be non-increasing degree sequence. So we define a sequence in the following way. So d star is another sequence whose entries are d1 star and so on. And each dk star is given by this relation. This is the cardinality. This right-hand side is the cardinality of the set, which contains I such that di is bigger or equal to k. Very simple technique. Here is an example. If d is this degree sequence, then d star will be this. So here you can see the suffix I, those i's will be put here, which are greater or equal to k for the kth entry. And this also plays a good role in this, in our problem, which we discuss just a short while after some slides. And we have the conjugate sequence here, which is called as conjugate degree sequence. Why it's called as conjugate degree sequence? Because it has been obtained for a given degree sequence. And if we apply the Schur's theorem on this conjugate degree sequence and the Laplacian eigenvalues, we will see that there will be a majorization relation between the degree sequence and the Laplacian eigenvalues. So the degree sequence of a graph G is majorized by its conjugate degree sequence. This can be seen easily from the theorem below. We have this theorem which says that the degree sequence is always majorized by conjugate degree sequence. So degree sequence here is majorized by conjugate degree sequence. Let's see this relation. Now, as defined, this di star, the conjugate degree, which is given here. So it means degree of vertex V is bigger or equal to I. Then we form this sequence. And let's assume that ignoring this first two lines for a second or two, if we take the Laplacian eigenvalues and we take, like we said, that the Laplacian eigenvalues can be put in the form mu1 is bigger or equal to mu2 is bigger or equal to mu3 and so on. The lowest one is mu_n. And we go on taking the sum, like sum of k largest or sum of two largest. That means the largest and the second largest if they are added. Let's denote the sum of k largest Laplacian eigenvalues, which is this summation, mu I want k by skg. So we put this skg in our mind because in many slides now we'll be discussing this skg. This is the sum of k largest Laplacian eigenvalues of a graph. So we apply Schur's theorem. That Schur's theorem or Schur's inequality says that Laplacian spectrum majorizes the degree sequence. Let's keep this in mind. This is one relation. Laplacian spectrum majorizes the degree sequence. Another theorem, which is Gale-Reiser theorem, that says that conjugate degree sequence majorizes degree sequence. So we have two important relations. Schur's inequality says Laplacian spectrum is majorized by degree sequence. Gale-Reiser theorem says conjugate degree sequence is majorized by degree sequence. The question is follows: whether the Laplacian spectrum and the conjugate degree sequence are majorization comparable. That means here we have two relations. Can this Laplacian spectrum be majorized by the conjugate degree sequence? So it says that here it says something like A is majorized by B. Here it says something like B is majorized by something else. And can we have a relation of this type, which was raised by Graf and Maris in 1994? The question was, is Laplacian spectrum and conjugate degree sequence majorization comparable? Or in other words, we can say, does there exist some majorization between these two sets? So this was the theorem proved by Graf and Maris that time. That is, the sum of k largest Laplacian eigenvalues can be majorized by the conjugate degrees. This skg is nothing but summation of mu I. So this is the left hand side is summation of mu I is smaller or equal to this quantity. That means this has been, actually it was a conjecture for a long time, from 1994 to something like 210-11. So it was proved only in 211 by By, and this paper appeared in Transactions of American Mathematical Society in 2011. So it gave proof to this conjecture. That's why it's now called as Graf-Maris theorem. So it's written here, it was proved by By. And what Brouwer did now, we come to our conjecture. He put an analogous conjecture. In 2012, it was something like this. Imagine we have a graph with order n and size m. Then for any k, this sum of k largest Laplacian eigenvalues always remains less or equal to m plus k plus 1 choose 2. This is the first problem, which is the main concern of this talk. So why it is still unsolved, why it's interesting, why it goes to several directions, because while dealing with initially, when we put forward a conjecture, every one of us, when we put some conjecture, we actually sometimes do not know how important it will be later on. Now, this conjecture has been connected to several other spectral graph theoretic problems. And it is assumed that if we get a solution for this Brouwer's conjecture, we may in fact land on solving some more problems. So what is the observation here? The first thing is why it is difficult to work on this conjecture. You can see by the relation itself, the difficulty is here in the left hand side, we have k largest Laplacian eigenvalues. And we say that it is smallest, less or equal to m plus k plus 1, choose 2. We know that m is the size of the graph. It is given to us. And this k depends on how many Laplacian eigenvalues sum we are choosing. So sum of k largest Laplacian eigenvalues. So this k is not a problem with us. This k plus 1 or this k is actually what we choose here in the left hand side. So it actually remains only m. That is the size of the graph, which in other words means that the conjecture wholly depends on the size of the graph. We don't have any other parameter. There is the difficulty. The difficulty becomes lesser if we add some more parameters, graph theoretic parameters. But then it is not this conjecture. There will be bounds, stronger bounds, involving more than one, like someone can come and he can say that this sum of k largest Laplacian eigenvalues is less or equal to something like m plus some other parameter like n, like chromatic number, like independence number, like matching number. So many graph theory parameters can be involved, but that actually is not the conjecture. The conjecture is extremely in terms of the size. So this is the level of difficulty here. Now, what people have been doing for the last 10 years, although this conjecture has been now solved for several families of graphs, we cannot have a direct proof or direct verification of this conjecture for any graph. So what we do as a student of spectral graph theory, we check it for certain families of graphs. And then maybe sometime it may lead to a bigger thing. And when we deal with smaller families of graphs, what interesting thing we obtain, it means we know the family of the graph, we know other parameters also. So initially our goal is to get some bound for SKG in terms of more than one parameter. And then the important thing is, are we able to eliminate that parameter which is not in the conjecture? Say, for example, if I get some upper bound, some bound like this upper bound in terms of m and n, the order of the graph. So is there a technique with me? I can ultimately eliminate n. So if n is eliminated, the bound will be here. And we have been reasonably successful in several families of graphs. Other people are also working, and the breakthrough or the success will be discussed from stage to stage. And this one is the latest development of this conjecture, what has been done up to this stage. So by simple calculations or computations on the computer, Brouwer himself checked that this conjecture is true for all graphs with 10 vertices, up to 10 vertices, so smaller graphs. So these observations also validate the conjecture. That is, maybe it will be true. And then again, if we see the Setkovic-Dub's book on algebraic graph theory, it will be very easy to see that the conjecture is true if we take this sum of all Laplacian eigenvalues, that if k is equal to n or n minus 1. Again, the result is true for k equal to 1 if we take the largest one. The largest one is always true because it's always less or equal to n, and hence we know that the conjecture is true for k equal to 1. Sometimes I may write BC, which represents Brouwer's conjecture. Again, proved for regular graphs, those graphs whose degree is same. Like we have a cycle of length 4, we have a cube whose degree of each vertex is 3. So this is true for all regular graphs. Hammers, Mohammedian, and Taifai in 2012 or later on proved this graph to be true when k is equal to 2. That means two largest Laplacian eigenvalues. It was also not easy to prove for k equal to 2 because k equal to 2 means the largest one and the second largest one. They proved that this conjecture is true for all trees. So this also has gone. And some observations about this: if G satisfies Brouwer's inequality like Brouwer's conjecture, then the complement also does the same thing. So it's true for complement also. If it's true for two graphs G and H, their union also satisfies Brouwer's conjecture. This is true for co-graphs also, the graphs I mentioned earlier. And then this is true for complete k-partite graphs also. And why it is true for complete k-partite graphs, it will be easily obtained for co-graphs. You can see here, the reason is that a complete k-partite graph is always a co-graph, because complete k-partite graph will not have P4 as a path, as an induced subgraph. Later on, Fischer, Hoppen, Rocha, and Trevisan in 2011, but that was later in 2011. They published a paper on the title on the sum of Laplacian eigenvalues of a tree. So they found actually an upper bound like this. You can see this is not Brouwer's conjecture. This is an upper bound if there's a tree T which satisfies this upper bound. It's always less or equal to n minus 2 plus something and plus something. And when k is equal to 1, this equality always occurs in this type of tree. That is the star. You will see here this bound is in terms of n. As I earlier said, our attempts will be to find this upper bound, maybe in more than one parameters, ultimately see if we can eliminate the parameter and arrive to Brouwer's conjecture. So with this bound, later on we use this bound. At the same time, in 2012, Du and Su obtained bounds for this SKG, and then they proved that this Brouwer's conjecture is true for unicyclic and bicyclic graphs. So this family is also completed. Unicyclic means those graphs having one cycle, and bicyclic means those graphs having two cycles. They are a bigger class of graphs. Rocha and Trevisan in 2014 continued their work, and they found bounds for this SKG, which improved the bounds of Du and Zu, the earlier bounds, the bounds in the last slide. So with those improved bounds obtained by Rocha and Trevisan in 2014, they verified this Brouwer's conjecture in the following cases. So this was true, like when we say k is the sum of largest Laplacian eigenvalues. This k, they proved it if this k lies between 1 and g divided by 5. This is the function. So this is the ceiling function, g divided by 5. So if this k lies between, g is the girth, that means the smallest cycle. So if we know the girth in the graph, and they proved this for those values of k which lie between 1 and this. And then next, what happened? For a connected graph G with maximum degree delta having p pendant vertices and c cycles, they also verified this conjecture for this family of graphs having maximum degree delta p pendant vertices for all delta greater or equal to c plus p plus 4. Okay, we defined clique earlier. It's a complete subgraph, and clique number is the cardinality of the maximum. It's the cardinality of that maximum clique, and the cardinality of maximum clique is the clique number. We denote it by omega. So we remember this parameter here, the graph invariant, that's omega. We define another graph invariant, which is vertex covering set, which will come from this vertex covering set. So when a subset of the vertex set is set to form this vertex covering set, so if we say that the set of vertices, the subset of the vertices will be vertex covering set if each edge of the graph G is incident to at least one vertex of that set. We have analogous definition for edge covering set also, but we'll be mostly interested for this vertex covering set here. So this covering set with minimum cardinality is called the minimum covering set, and it will be denoted by tau. So we have now introduced two these invariants. One is omega, one is tau. With the help of these two invariants, Du and Zhu in 2012 obtained this estimate for this sum of k largest Laplacian eigenvalues. They in fact proved that it always remains smaller or equal to this k times omega, and you will see this is all in terms of m and omega. So we can no way say that this is Brouwer's conjecture. Yes, this can be Brouwer's conjecture if we eliminate this omega here, but then things will drastically change. And in 2015, Das, Mojalal, and Gutmann obtained the estimate for SKG, which is m plus k tau. Here again, you will see this tau is getting involved. This is creating problems. So from these two bounds, it will be important if we can eliminate omega and tau here. So something which is connected to our contribution, supposing we take this sigma, which lies between 1 and n minus 1, this sigma will be is the number of Laplacian eigenvalues which are greater or equal to the average degree. So, well, average degree is 2m by n. So if we take this average degree of the graph and anything which is greater or equal to 2m by n, we put here it as sigma. And then with this sigma, we have obtained this bound in 2015. So this means it's not k largest Laplacian eigenvalues, it's sigma largest Laplacian eigenvalues. So you see how we are trying to come to this problem from various sides. So this is sigma here, where sigma is given by this, those Laplacian eigenvalues, is the number of those Laplacian eigenvalues which is greater or equal to the average degree. And once we prove this, you can see here, sigma is here, omega is here, delta is here. So many graph invariants involved here. And then we see, are we able to eliminate these parameters? So for elimination, we have three types of families of graphs. One is gamma 1. It's the family of all connected graphs where these conditions satisfy. I will show you by a figure how they look like. The graphs in the family gamma 1. It looks like this. So these are all graphs with a clique here, and we have these pendant vertices. This is our gamma 1. And we obtained an upper bound for the sum of k largest Laplacian eigenvalues for graphs belonging to gamma 1. So this is true for the whole family of graphs which are in gamma 1. It is a large family of graphs. And you can again see this estimate is in terms of tau, omega, and m. Again, two additional parameters are there visible. It's tau and omega. Now, what was the benefit of this upper bound or this inequality? We were able to verify Brouwer's conjecture for new classes of graphs. That's the gamma 1, the family of gamma 1, where the graph is of now bigger order. It's n greater or equal to 24. So we have actually proved the Brouwer's conjecture. We have verified the Brouwer's conjecture for all those graphs in gamma 1 whose order is bigger or equal to 24 and have clique number omega bigger or equal to 7n by 8. Means that the largest complete graph as a subgraph, its order is 7n by 8 or more. So, and we were able to verify this conjecture. You can see here, we have proved SKG is less or equal to m. We have eliminated all the graph invariance. Then we take another family, gamma 2, which looks like this. This is our family of graphs. They are called as gamma 2. They belong to gamma 2. And gamma 3, they look like this. So it is complete bipartite graph here, and we have a cycle here. We have a cycle here, and all other vertices are pendant vertices. We were able to verify Brouwer's conjecture for a large class of graphs in gamma 1, in gamma 2, and in gamma 3. That means this class of graphs, Brouwer's conjecture is true. Now, I don't want to go into the technical details of these graphs because it will take me another 10-20 minutes then. So then one is here, these classes of graphs, this class of graphs, then graphs belong to this class, and finally, not only this, we were able to have some more information. Now let's define a family of graphs, of course, from gamma 1. Those graphs from gamma 1 where we define where G is of order n with omega equal to tau plus 1. That means such graphs where the clique number is equal to vertex covering number plus 1. This relation, very important relation. For these graphs, Brouwer's conjecture is true. We have proved it in principle that Brouwer's conjecture is true for all graphs belonging to this class of graphs. And in 2019, we continued our work, and ultimately we were able to prove, firstly, we were able to obtain some more estimates and bounds for this sum of k largest Laplacian eigenvalues for more families of graphs. We are just increasing our domain of verification of this Brouwer's conjecture. And finally, we were successful in the following result. So you can see here, Brouwer's conjecture is true, Brouwer's inequality is true for those graphs where these properties are satisfied. And not only in 19 and 20, then we had some collaboration with Trevisan. He had started work earlier, like in 12 and 13 and 14. And this work started immediately after that ICM 2018, which was in Brazil. So we started doing something there. And ultimately, we had some results which were published, titled as Further Developments of Brouwer's Conjecture. And we proved it for two more families. One family was obtained from a clique of size omega by identifying each of its vertices to a vertex of an arbitrary C-cyclic graph. And the second family is composed of the graphs in which the removal of the edges of the largest complete bipartite subgraph gives a graph, each of whose non-trivial components are C-cyclic graphs. Again, these are two large families of graphs. This is the first one, it looks like this, and this is the second one, it looks like this. One more type of graph from the second family. And in this year, 2021, the latest shot played on this Brouwer's conjecture is that we obtained SKG in terms of the clique number and order of n, and the second result, and these two results helped us in verification of Brouwer's conjecture for several families of graphs, including the following. So these types of graphs. I just mentioned these figures so that we have a visual understanding of how these graphs look like. So these graphs we have proved for these. So this was my first thought of the lecture. So still there are like several other results which have appeared in the literature, and I have not included them deliberately because it will have been longer. There are like one paper I recently was able to see. It was titled like Constraints in Proving the Brouwer's Conjecture. So he has discussed some constraints here. But I think that we can have like, people can work on this again, because still there are many families which are untouched. And maybe now the natural question will be in our mind, okay, why we are doing with these smaller families of graphs or bigger families of graphs? Is it a matter of just publication or having the papers, the number? No, it's not like that. we are actually targeting, can these smaller families lead us to some bigger thing? And if we have proved something for a smaller family, it should be published, because people will know that we have proved for this family. They will not waste time on that family. And secondly, they will understand the idea, so that these ideas will be shared to different people. And ultimately, maybe sometimes someone will come with a reasonable proof for this conjecture. So I move to the second problem, that's Laplacian energy. Now, coming to this history of this Laplacian energy, it comes from actually graph energy. Now, just 2 minutes on graph energy. Once we have an adjacency matrix, we have the adjacency eigenvalues. Same problem is there, how to find these adjacency eigenvalues. And then the person whose name is written here, Gutmann, he is a Serbian physical chemist. He was dealing with Huckel's molecular orbital theory. So he needed to get the energy levels of the molecules and so on. So there were their own methods of calculating such energy. But ultimately, he found a connection that this energy can be mathematically calculated also. So what was the way of doing or calculating the energy? It was like modeling the molecular like the molecule, the hydrocarbons, by a graph. Once we have a graph, and then we have the adjacency matrix, and then taking the absolute value, taking the sum of the absolute values of all the eigenvalues, the adjacency eigenvalues. Once we take the sum of all those absolute values, whatever the result was there, Gutmann checked it that it was nothing but it was the energy level which was discussed in Huckel's orbital molecular theory. There is a verification, there's a proof how it is equivalent. So chemists started working on it. Now we have so many of hydrocarbons existing in nature. Every time they needed that energy, every time different graph was coming into existence. And other set of people who were pure graph theorists, they, like me, we didn't have to do anything with chemistry. We just used to pick up the types of graphs and see what can be done with that graph, what can be the energy of that graph, or that family of graph. Will the energy increase on removing a vertex or an edge, or will it decrease, or what more information we can get? Now the question is, getting that energy, we require to know each eigenvalue individually. That's not possible. So these graph theorists, including Gutmann, they devised some other methods where we didn't need to get each eigenvalue individually. They had a direct method, like how to get the Laplacian energy, how to get the sum of absolute values directly without knowing each value. So one such method was with the help of integration. But then again, some constraints were there, because if the integral turns out to be improper one, which is not solvable, then we were looking for other methods also. And later on, so this is about the energy of the graph. There are many papers written on this energy. So many open problems are also there. Now, once this Laplacian matrix was given, people started thinking about, can be there a Laplacian energy type of thing in mathematics or in chemistry? Yes, the connection was given. Laplacian energy was again put forward by Gutmann and Zhao in 2006, and they defined this Laplacian energy as the sum of these absolute values. Here it is not only the adjacency eigenvalue which was in adjacency matrix, it is Laplacian eigenvalue minus the average degree. And it has been found that this quantity is an extension of graph energy concept and has found remarkable chemical applications beyond the molecular orbital theory of conjugated molecules in 2007 by Radenkovich and Gutmann. So that time they formulated the following conjecture. That is, this Laplacian energy of trees, this is conjecture only for trees, this Laplacian energy of any tree lies between the Laplacian energy of a path and the Laplacian energy of a star. Path is a tree, star is a tree. So the conjecture says that choose any tree, its Laplacian energy will be between the Laplacian energy of a path, which is easy to obtain, and Laplacian energy of a star, which is again easy to obtain. What are the recent developments for this conjecture? Trevisan in 2011 proved this conjecture to be true for all trees with diameter 3, and also showed by direct calculations that this conjecture is true for trees up to 18 vertices. And then Fisher and other people also proved that the right inequality of this conjecture, because it has two parts of this conjecture, the left inequality and the right inequality. I can show you once more. Right inequality is the Laplacian energy, the upper bound is, or it's bounded by the Laplacian energy of the star, and it's bounded below by the Laplacian energy of a path. And this was true for, the right inequality was true for all trees of order n. So that means this part is now solved. The upper bound is solved. What remains? The lower bound of this conjecture. And Chang and other people in 2012 verified the left inequality for trees of diameter 4 and 5. It's not proved for all graphs. It's all trees. It's proved for trees with diameter 4 and 5, but with perfect matching, which means that they were not able to prove this for all trees of diameter 4 or all trees of diameter. They verified the conjecture for only those trees which had diameter 4 but also had a perfect matching. And then Rahman and other people in 2019 considered some families of trees of diameter 4 which were not chosen by Chang, and verified the truth of inequality of conjecture for trees of such families. And in 2021, we verified the left inequality for all trees of diameter 4. So the condition having perfect matching is altogether removed. So we have proved this for all trees of diameter 4 and some cases of diameter 5 in this paper, which recently was accepted by discrete mathematics, algorithms, and applications. And this conjecture is also still open. So I think I would like to know how many minutes I have, or I should stop here.
Okay. So, okay, so thank you very much, Professor PIRZADA. So this is the end of your slide, or you want to add one more things?
No, then it will take me another 5-10 minutes.
Okay, good.
So I would like to stop here.
Oh, you want to stop? Okay. So
Stop here.
Okay.
So
Great.
just one this reference, which is my book on graph theory. And you can see it here. It looks like this color.
Oh, okay.
It was published in 2012, and we have been using it here also.
Okay.
So thank you very much. Thanks for your kind attention.
Okay, so give applause to Professor PIRZADA. Very comprehensive and interesting lectures. So I like to invite some questions. If there's some question or comments or remark, just raise hand.
Assalamualaikum.
Yeah, okay. Please, Bu Monica, yeah?
Yes.
Yeah.
Okay. Thank you, Prof. Thank you for the interesting presentation. I'm PhD student in University Putra Malaysia, but I'm from Indonesia.
Oh, okay.
Currently, I'm working with energy of commuting and non-commuting graph. But I don't use the adjacency matrix, but I'm using matrices that related to the energy of the graph. And I'm thinking, because of your presentation, if I replace the adjacency matrix in your definition of Laplacian matrix, could I replace that adjacency matrix to the matrix related to the degree? So maybe I can modify the name of Laplacian degree matrix, something like that. This is the first question. And then the second question is, I read the paper of Goodman, and they prove, not prove, they provide the conjecture that the adjacency energy is always less than or equal to Laplacian energy. But in non-commuting graph for dihedral group, it is not true, because it is always not equal between adjacency energy and Laplacian energy. So because of that, I'm thinking to replace the adjacency matrix in that definition. I want to know what is your opinion if I do that. Thank you.
Okay.
So you want to replace this adjacency matrix by Laplacian matrix? Is this the question, or you want to replace adjacency matrix by any other matrix?
I replace the adjacency matrix because Laplacian is equal to D minus A. I want to replace the A matrix.
You want to replace matrix A there?
Yes, yes.
By which matrix you want to replace?
For example, degree sum matrix.
Okay, okay. So I understand. So it will be something like maybe the new matrix which comes,
yes.
Maybe it is not discussed earlier. So in case it's a new matrix, it will be fine to work in that direction. But the important thing is what connection you will give to that energy. Will that energy be only a theoretical work, or will it have a connection to some older energy, like energy of a graph, Laplacian energy of a graph, or some different concept from chemistry or physics or something else? Doing straight away, like if you define just energy, replacing a matrix and doing energy, the people will ask you questions, how this graph is useful, how this energy is useful, what connection this energy has with the previous energies. So if you are not able to find the connection with chemistry, but at least you have to find a sound connection with the older energies, then only you can say, look, we have given a new matrix, we have a new energy, and it gives something about the older energies. Then it will be okay to work in that direction. And secondly, the second question, like you said that the energy is always less or equal to the Laplacian energy, and you have a counterexample. So if this is a counterexample, you can just go and submit it to somewhere and say that this conjecture is not true. And you have a counterexample in the form of commuting graphs.
Yes. I submitted. I'm waiting the reviewer.
Okay. Okay.
Yes. Thank you, Prof. Thank you.
Okay. Thank you, Mika. Any other questions or comment? If not, I'm having one or two questions as a moderator. Okay, so
may I ask some question?
Oh, okay, we'll do then. Okay, we'll do. Yeah.
Thank you, Professor PIRZADA, for your very comprehensive and inspiring talk. I was wondering about the browser's conjecture. So the beauty of the conjecture is that because it depends only for, two parameters, the number of the edges and k. I was wondering for the families of graphs that have been proven satisfying the conjecture, is there any graph that also attains the equality?
Yeah. So there are many examples.
many examples of that.
You will see wherever it has been proved, every person there writes at the bottom the equality holds if and only if the graph is isomorphic to some graph. So exceptional cases are always there.
All right. Okay. So that means that the conjecture also the best I mean it very good bound.
Yeah.
Not only depends on a few parameters, but only all right. Just one small question about the split graphs and the threshold graph. It's also Laplacian integrals or not?
Which one?
Split graphs, and you mentioned about
Yeah. They are Laplacian.
Oh, they also both
Laplacian
also Laplacian integrals. Okay. Okay. Thank you, Professor PIRZADA.
Okay, thanks, Hilda. Any other questions?
One question, please.
Yeah, please. Pak Nengah.
Thank you so much, Prof. Edy.
Yeah.
Very nice presentation from Prof. PIRZADA. Do you have any experience of distinguishing the possibility of having dense graph and non-dense graph in terms of Brouwer conjecture? Which one is likely possible to satisfy the Brouwer conjecture?
Yeah, there is one paper which appeared more recently, some years back, couple of years back, where there was given the probabilistic approach of Brouwer. It was mentioned that this Brouwer's conjecture is true for almost every graph with the help of the distributions, probability distributions, and where these types of graphs, dense graphs, were used. So this will be really interesting to see whether it will be for dense or non-dense. And definitely it will lead to something like the probabilistic approach of solving the problem.
Okay, thank you.
Okay, thank you, Pak Nengah, for the questions. Anyone? So any other questions or remark? Okay, I'll have two questions, Prof. PIRZADA.
Yeah.
Regarding the subdivision, you state that for the subdivision of graph G, having Laplacian integral as a Laplacian integral is if and only if G is complete graph, right?
Right. Yeah.
So that means for any graph with having more than 2 vertices of degree 2 will be not Laplacian integral, right? Is it correct? Or
you mean to say, let me go to that part.
Yeah. Yeah.
Here.
So this is a theorem by Gron and Meris.
Yeah.
So the characterization is only if G is a complete graph.
Yeah.
So that means any graph with more than 2 vertices or more with degree 2 will be not Laplacian integral. Is that correct?
No, this is here when we say SG is Laplacian integral.
Yeah.
Now this SG is not the original graph. Actually, SG is obtained from G. So the being Laplacian integral for SG or not a Laplacian integral for SG depends on the original graph when it's K. And that means if we have a complete graph, of course, with greater or equal to 2 vertices, we have a complete graph. When we subdivide each edge, then only it can be Laplacian integral.
Oh, you subdivide each, yeah? Every edge.
Yeah, each edge.
Okay. Sorry. I thought it's only one edge. Okay.
One edge is for GN.
Yeah, I thought it's only one edge, that one. Okay, every edge. Yes. Okay, thank you. So, okay, so that's the first question. The second about Brouwer conjecture. This is very interesting. Is there any lower bound, or the lower bound is not interested? Not interesting?
Lower bound for
yeah.
this, yeah,
On
it's
the
also
Brouwer,
interesting.
for the
So,
Brouwer conjectures.
As far as we have the information, there do not exist lower bounds of the type of Brouwer's conjecture, but we have put forward one lower bound, if I have mentioned here or I missed it.
Okay.
I really do not remember. I have.
Okay, but
I missed it. But there we have proved one lower bound.
Right.
That was in the same paper. That was in the same paper in this paper, 2016 paper.
I see.
Only one lower bound, and thereafter again we didn't see any lower bound.
Yeah. Okay, good. And one more question about the Laplacian energy. So the conjectures is only for three.
It's only for trees.
Yeah. What about for other graph other than trees? Is there any conjectures?
We don't have such type of conjecture for other types of graphs, but can be formulated. But then it will be a very, I can say, the level of difficulty will be more there in other types of graphs. We can put forward something like that. Although the bounds are there, both lower bounds and upper bounds, but something like this conjecture that, like if we say that, suppose we have the family of unicyclic graphs. So in the family of unicyclic graphs, which unicyclic graph has the lowest energy and which unicyclic graph has the largest energy? So it can be formulated. And also, I would like to, it will be important to mention here, like the part which I didn't discuss here, there is an analogous conjecture from this Laplacian matrix to signless Laplacian matrix. If you remember, I gave the alternative definition for Laplacian matrix, which was degree matrix minus adjacency matrix. Signless Laplacian matrix is the degree matrix plus the adjacency matrix. So it would have been a question in mind, what happens to the matrix if we take degree matrix plus adjacency matrix? That matrix is there, it's called as signless Laplacian matrix. And the conjecture has been put forward, analogous conjecture, and analogous type of difficulty. Again, that conjecture has been seen to be true for certain families of graphs. Not only that, in 2019 or 20, we were able to put forward a similar type of conjecture for distance matrices, where instead of the adjacency relation, distance is important. And studying distance matrix is important because of the Wiener index of graphs. Wiener index, which is again having enormous applications in chemistry. So we have put forward that conjecture, and we have verified the validity of that conjecture in many families. That is online, that paper in linear and multilinear algebra, something about distance matrices. So people can think about, yes, there was a question in between which I used to discuss with my students. Like, we have been also studying spectra of signed graphs and spectra of directed graphs. There are other types of matrices. They have their own matrices. So we're discussing one time, is this conjecture something like this bound in signed graphs, spectrum of signed graphs? The moment we were discussing, we found a paper already appeared that there is a conjecture like this. But just after 6 months, that conjecture was disproved. There was a counterexample. Both papers appeared in linear algebra applications. So for the people who want to work on this, it's still open to make a conjecture like upper bound or lower bound for signed graphs. And a similar type of conjecture can be made for directed graphs, where in case of directed graphs, we have some other difficulty. The Laplacian eigenvalues cannot be always real. So some other thing comes into existence. So these types of problems can be dealt with all types of matrices also.
Okay.
And also interesting for the students is that if they work, their main focus should not be like on energy of graphs. Their main focus should be on spectra of graphs, the Laplacian eigenvalues. They should focus on spectra. The energy will be a bonus for them. It will automatically come from the spectra. So for this spectra, they can deal with this Brouwer's conjecture. Also, they can deal with the spectral radius, the largest Laplacian eigenvalue. Imagine if a student comes out with one theorem, giving a better bound for Laplacian spectral radius or spectral radius, it will be accepted worldwide. It's a very good area to work on.
Okay, thank you, Professor Pirzada. Bapak Ibu, is there any other questions? If not, then we can give applause again to Professor Pirzada for the nice and comprehensive lectures. Yeah. So, Professor Pirzada, thanks again for your wonderful lectures. I think everyone here enjoy your lectures, and we will give you some certificate.
Thank you very much.
So we will show this certificate, yeah, publicly. Silakan Bu Prita. Can you show the certificate for Professor Pirzada?
I couldn't do share screen. Please wait for a moment, please.
Siapa yang bisa? Nggak bisa? Oh, okay. Sorry.
No problem.
Share.
Huh? Can you? Okay, let me see. Oh. Just a moment. Yeah.
Bapak bisa saya dijadikan host yang satunya lagi, Pak? Account saya yang satunya lagi.
Oke. Ini sekarang sudah. Oke, I'll show this one.
Oh, Prita ada 2?
Iya.
Ya, mana satu lagi? Saya nggak bisa ya, harus Pak Edy.
I'm sorry.
Okay.
Oh, iya.
Okay. So this is the certificate, Professor Pirzada. So thanks again for your lectures.
Thank you very much for the certificate. Well, you don't mention the title of the talk.
Okay. We will put now the title of the talk.
Thank you very much for this invitation again. I hope I can deliver some other time, some other lecture on some different topic.
Great.
I hope maybe after some months, because of the schedule and schedule we see, and I will be able to deliver altogether a different topic.
Okay.
Or that's something like some new things on the spectral graph theory.
That's wonderful. Thank you very much.
Thank you.
Okay, Bapak Ibu. So I think this is the end of our Combinatorics today series.
You're not taking a picture, Pak Edy?
Yeah. Oh, picture.
Maybe.
Okay. Before we end this series, now we take up pictures. Siapa ini? Bu Hilda bisa?
Oh, hang on.
Saya bisa, Pak. We will take picture. Okay, everyone, smile.
Oh, hang on. I think some of us haven't.
Oh, yes, please turn on the camera. Yes.
Yeah.
Okay. Okay. 1, 2. Some of them. Okay. 1, 2, 3. Okay. Once more. 1, 2, 3. Okay. Thank you very much.
Okay.
So I should leave now
for the talk.
So thank you everyone.
Thank you.
Terima kasih Pak Edy.
Terima kasih banyak semuanya.
Sampai ketemu nanti malam Bu Kiki.
Bu Kiki.
Thank you very much.
Terima kasih.
Terima kasih Bapak Ibu.
Semuanya. Terima kasih ya.